Statistical Process Control SPC, bringing data-driven quality and stability into continuous operations. Statistical process control is a powerful methodology for monitoring and improving process performance through statistical analysis. Originally developed for discrete manufacturing, SPC has now evolved into a critical layer within modern control architectures for continuous and batch processes. By detecting process shifts, identifying abnormal variations, and guiding corrective actions, SPC enhances both product quality and operational consistency. In today's data-rich industrial environments, SPC no longer exists in isolation. It is increasingly integrated with automatic control systems, predictive analytics, and digital twins to enable closed-loop quality assurance in real time. #track why SPC matters in modern process industries. Advanced control systems aim to maintain stability, but they operate on engineering logic and physical models. SPC complements this by offering a statistical lens on process performance, detecting subtle shifts that may be missed by model-based controllers alone. Benefits include early detection of process drift before specification limits are breached, reduction in raw material usage, energy, and rework through tighter quality control, enhanced compliance with regulatory and quality standards, better understanding of process capability and control effectiveness. When integrated effectively, SPC supports a predictive, proactive approach to quality and performance management. Forms of SPC in industrial automation. Conventional SPC, offline statistical control. Traditional SPC involves plotting process metrics over time using control charts, setting statistical control limits based on historical data, identifying assignable causes when values fall outside these limits, manually investigating and correcting root causes. Common tools include Shewhart charts, cumulative sum (CQ sum) charts, exponentially weighted moving average (EWMA) charts, range and variance charts. While effective, conventional SPC is passive and retrospective, making it less suitable for fast-changing or continuous processes. Algorithmic SPC, ASPC. To overcome the time delays in conventional methods, algorithmic SPC embeds statistical logic within the automation system. Here, real-time data from sensors is continuously analyzed. SPC techniques run alongside feedback controllers. Deviations trigger alarms, overrides, or adjustments. ASPC enables real-time surveillance of control loop performance, enabling operators and systems to intervene before product quality is compromised. For example, a compressor's discharge temperature trend triggers SPC-based alarms for fouling. Reactor yield variations initiate root cause analysis via integrated SPC metrics. Active SPC, online statistical control. Active SPC takes integration a step further by allowing statistical logic to directly influence control actions. It differs from conventional control in that corrections are applied only when statistically significant deviations are detected. Control effort is minimized, reducing wear and utility consumption. The control system behaves like a hybrid between SPC and feedback control. In this approach, SPC becomes the primary control engine, not just a monitoring layer. It is especially useful in slow processes or batch operations where continuous adjustments may be unnecessary or counterproductive. Modern enhancements to SPC. With the rise of industrial AI, machine learning, and cloud computing, SPC systems have become more intelligent and connected. Key advancements include multivariate SPC, MSPC, using tools like Principal Component Analysis (PCA) to monitor multiple variables simultaneously. Anomaly detection models trained on historical process data to catch new or rare faults. Integration with manufacturing execution systems, MES, and enterprise resource planning (ERP) for traceability and auditability. Dashboards and mobile alerts that visualize SPC performance metrics and distribute alerts in real time. SPC is also a foundational element of quality by design, QBD, and process analytical technology, PAT strategies in regulated industries such as pharmaceuticals and food processing. SPC in a digital control hierarchy. In the modern control stack, SPC sits across multiple layers. At the base level, monitors loop stability, sensor drift, and valve performance. At the supervisory level, tracks KPIs like yield, emissions, cycle times. At the business level, feeds statistical summaries to dashboards and reports. It coddled predictive control MPC by adding statistical reasoning, fault detection and diagnosis, FDD, systems by highlighting abnormal trends, optimization systems by validating variability reduction claims. Statistical process control has evolved from a manual charting tool to a real-time integrated quality intelligence system. In the context of advanced control, SPC provides a statistical backbone to model-based logic, enabling smarter, more adaptive, and more robust control environments. As process industries continue to adopt digital transformation, SPC plays a key role in ensuring that control excellence translates into quality assurance, delivering consistency, traceability, and value across the production lifecycle. Dealing with data problems, strengthening control systems through data integrity, estimation, and analysis. Advanced control systems rely on data as their foundation. From model development to real-time optimization, every decision, prediction, and correction depends on data quality. However, in industrial environments, data is often incomplete, noisy, delayed, or unmeasured altogether. These challenges can degrade the performance of even the most sophisticated control strategies. Addressing data issues is not optional. It is essential. Modern control architecture must embed data validation, estimation, and conditioning techniques to ensure the reliability and robustness of control decisions. This forms a crucial bridge between physical sensing, digital models, and automated action. Key data challenges in process automation: lack of direct measurements for key quality variables, delayed or infrequent sampling, especially when lab results are used, sensor drift, failure, or calibration errors, noisy signals and outliers, high-dimensional data with complex correlations, poor input-output pair selection for controller design. Unaddressed, these issues lead to misleading model outputs, instability in control loops, inaccurate process optimization, missed faults or false alarms. Modern solutions to data problems: inferential estimation, soft sensors. Many critical variables, e.g. viscosity, product purity, fouling rate, are not directly measurable online. Inferential estimation, also known as soft sensing, uses secondary measurements, e.g. temperature, pressure, flow, to estimate unmeasurable properties in real time. Modern inferential techniques include linear regression models, partial least squares, PLS regression, neural networks and machine learning, ML, hybrid physical data models. These estimators are trained using historical data and validated against lab results. Once deployed, they act as virtual sensors, feeding real-time estimates into controllers, dashboards, or alarms, filling critical data gaps. Control systems are sensitive to data anomalies. Even a single spike or faulty reading can cause controller overreaction or trigger false trips. To mitigate this, signal filtering, low-pass Kalman filters, smooths noise. Outlier detection removes spurious data points. Voting logic or redundant sensors improve confidence in critical readings. Logic-based filters combine statistical thresholds with control knowledge to validate inputs. In safety-critical applications, redundant sensor architectures with automated validation are used, e.g. 2 out of 3 voting logic. In less critical systems, intelligent filtering balances noise rejection and signal responsiveness without introducing harmful delays. Data analysis and input-output mapping. Before building control models or configuring loops, engineers must understand how variables interact. This includes identifying which variables influence each other, how changes in one affect another, causality and direction, whether the relationships are linear, nonlinear, or time-varying. Modern analysis tools include correlation analysis and covariance matrices, scatter plots, box plots, and heat maps. Principal component analysis, PCA for dimensionality reduction, relative gain array, RGA, and singular value decomposition, SVD for multivariable loop interaction analysis. These tools help determine appropriate manipulated variable, controlled variable pairings, whether a system needs single input, single output, SISO, or multivariable control, MVC, whether a nonlinear or hybrid model is more suitable than a linear one. Integrated data management in control environments. Modern control systems integrate data workflows from sensor to enterprise using real-time data historians for structured time series storage, data lakes for unstructured or high-volume sensor datasets, edge computing to process, validate, and analyze data near the source, cloud analytics platforms for model training, tuning, and visualization, digital twins to simulate missing or faulty data scenarios and validate control logic. These platforms enable faster deployment of models and controllers, online retraining of estimators as conditions change, lifecycle tracking of sensor health, data quality, and estimation accuracy. Conclusion. In an era where data drives control, managing data problems is as critical as designing the control algorithm itself. Modern plants must embed a data integrity layer comprising soft sensors, validation logic, and input-output analysis within their control architecture. By doing so, organizations enable more accurate, robust model-based control, smarter, safer decisions under uncertainty, scalable, self-improving automation systems. Ultimately, solving data problems transforms control systems from reactive tools into intelligent, data-aware digital ecosystems capable of delivering sustainable performance. Higher-level operations. Integrating optimization, monitoring, and intelligence beyond local control. Modern process automation is no longer confined to maintaining set points at the unit level. Higher-level operations expand the scope of control systems to address broader goals: economic optimization, fault management, production scheduling, and decision support. These supervisory functions reside above traditional PID and model-based controllers, forming an intelligent layer that links plant floor automation with enterprise-level objectives. With advances in computing, connectivity, and AI artificial intelligence, higher-level operations have become increasingly modular, scalable, and integrated into day-to-day process management. This evolution has shifted the paradigm from isolated control systems to coordinated, plant-wide performance orchestration. Key functions of higher-level operations. Process optimization. While local control loops keep variables stable, optimization systems adjust operating targets to maximize economic performance. These systems minimize raw material and energy usage, maximize throughput and product yield, align production rates with market demand or plant constraints, coordinate multiple units for integrated performance. Optimizers typically use steady-state models for computational tractability, with outputs feeding set points into the DCS distributed control system or APC advanced process control layer. In many cases, optimization is done on rolling horizons, blending real-time process data with business KPIs, key performance indicators. Technologies used include linear and nonlinear programming, LP/NLP, constraint-based solvers, real-time optimization, adaptive or economic MPC, model predictive control, chat process monitoring and fault diagnosis. Higher-level monitoring systems provide early warning, root cause analysis, and diagnostics. These systems continuously compare measured data with models or expected trends, looking for deviations that indicate potential problems. Functions include fault detection, e.g., valve sticking, sensor failure, leak detection, fault location and classification, condition-based maintenance and alarm prioritization, performance tracking, e.g., efficiency loss, emissions drift. Approaches range from model-based observers to machine learning algorithms, often supported by data historians and multivariate analysis. Monitoring and diagnostics help maintain plant reliability, reduce downtime, and support safe operation, especially in complex, tightly integrated systems. Intelligent supervision and decision support. Intelligent supervisory systems serve as the bridge between automation and human decision-making. Using artificial intelligence, AI, and knowledge-based systems, they analyze process trends and recommend actions, provide operator guidance and alarm rationalization, coordinate plant-wide responses to disturbances, automate routine supervisory tasks, e.g., controller tuning, set point updates. Core technologies include expert systems based on rule-based logic and inference engines, real-time knowledge-based systems, RTKBS, digital twins that simulate operating scenarios for decision testing, genetic algorithms, fuzzy logic, and hybrid neural symbolic systems. These systems enable operations teams to make informed, context-aware decisions, even in the face of uncertainty, incomplete data, or conflicting objectives. Hierarchical architecture of modern control systems. Higher-level operations are embedded in a layered control hierarchy, typically comprising Level 0 to 1, field devices and basic control, sensors, actuators, PID loops. Level 2, advanced control, MPC, multivariable control. Level 3, optimization and supervision, RTO, fault detection, intelligent agents. Level 4, enterprise integration, MES, ERP, planning and scheduling. Information flows bidirectionally. Upper levels provide goals and constraints, while lower levels feed real-time measurements and status. This enables vertical integration of production and business systems, agile response to market and operational changes, closed-loop coordination between production and profitability. Integration technologies and platforms. Higher-level functions are implemented through a combination of manufacturing execution systems, MES, enterprise resource planning, ERP interfaces, process analytical technology platforms, cloud-connected dashboards and analytics services, edge computing for local intelligence and data fusion. These platforms enhance collaboration across departments, engineering, operations, maintenance, and management, by providing real-time visibility, optimization insights, and actionable intelligence. Conclusion. Higher-level operations elevate automation from a collection of control loops to a strategic asset for plant-wide performance management. By integrating optimization, diagnostics, and AI-driven decision support, they enable more profitable and sustainable operation, faster problem identification and resolution, better alignment between production targets and business priorities. In the digital era, advanced control does not end at maintaining stability. It extends into plant intelligence, continuous improvement, and agile response, redefining how industrial systems are operated and managed.